earthquakes, let's go ahead and look at this Arctic News article. This is from Sam Carana's blog called arctic-news.blogspot.com. This is his latest post. It's from Tuesday the 14th. And the title says, Arctic hit by 10 tipping points. So fasten your seatbelt. Tipping points are abrupt climate changes that typically occur as self-reinforcing feedback loops start to kick in. 10 tipping points look set to hit the Arctic hard. Such tipping points can coincide, and they are in many ways interrelated, making that the danger is compounded by the domino effect of tipping points hitting one another. Number 1, El Nino. March 2020. This is from NASA LOTI. Centigrade anomaly versus 1951 to 1980. And he says the above image shows March 2020 temperature anomalies featuring very high temperature anomalies over Russia and over the ESAS, that's the East Siberian Arctic Shelf. Look at that. So that's in the brown range. So between 4 and 8.4 degrees Celsius higher than normal. But look at the United States and Canada. That's between 2 and 4 degrees. And the reds, look at all the reds. It's like half the globe is in the red. Looks like all the Arctic is in the red. High sea surface temperature anomalies along the path of the Gulf Stream. Right here. And look in the Gulf of Mexico. Global warming is a catastrophic development, and El Nino is global warming on steroids. As the Atlantic Ocean heats up along the path of the Gulf Stream, huge amounts of hot water get carried toward the Arctic Ocean, as illustrated by above image. From here all the way up to the Arctic. Current conditions still are El Nino neutral. Since the temperature rise is amplified in the Arctic, a strong El Nino later in 2020 can hit the Arctic particularly hard, which can act as a catalyst that triggers further tipping points to get crossed, as also discussed in an earlier post. This can in turn cause a steep global temperature rise, as illustrated by the image on the right. And we've seen this before. And this is so this is where we are in 2020. In February we were above 2C, and in March we're back at right at 2C above baseline. Here's January, February, March. So the trend, though, he says, just depending on what happens, that it could be we'll hit 3C by early 2021. Here's 3C up here. and this line is 2021, so that'd be January. And humans can't live at 3C. The image below shows that on the northern hemisphere, the March sea surface temperature anomaly for 2020 was higher than previous years. So that's quite a bit higher if you look at the graph there. Okay, tipping point number 2. Latent heat loss or loss of buffer. Sea ice, hanging meters below the surface, has until now consumed huge amounts of ocean heat moving into the Arctic Ocean in spring on the northern hemisphere. As a result, there has been a huge reduction in Arctic sea ice volume over the years. Moreover, Arctic sea ice is getting very thin. The image below shows a sea ice thickness in meters comparison below between February 28, 2015 and February 28, 2020, i.e. forecast for February 28th run on February 27th. But before we go there, we'll look at this. This is Arctic sea ice volume. Now volume is different from extent or concentration. Volume is, counting all of the ice in the Arctic. So this is from April 13th, and it's at its record low right here. I mean, for this time of year, it's below all of the others, all the other years. So that's not good. Uh-oh, what'd I do? Here we go. So here, this is from the Navy view. This is the ice thickness in the Arctic. Here it was from 2015 in February, the end of February. And we can see the thicker sea ice down here near the northern coast of Canada and Greenland, where we got it actually into the black reddish, well, it's reddish brown blackish. That's 5 meters thick. And the green, this green is like 3 meters thick. So between 3 and 5 here. But here, for this year, same day, February 28th, look at the difference. It's so much thinner, and there's no sea ice that's in that dark brown. There's none. And just a little bit of yellow and a little tinge of red and a little bit of green along the coast. And it's mainly in the aqua and under. So it's mainly 2 meters thick and less when you come out. So that will melt quickly. The sun's up now, so that will melt quickly. Ocean heat is on the rise, particularly in the northern hemisphere. As the sea ice is getting thinner, there now is little or no buffer left to consume the influx of ever warmer and salty water from the Atlantic Ocean and the Pacific Ocean. As illustrated by the image below, there is a tipping point at 1 degree C above the 20th century average, i.e. there are indications that a rise of 1 degree C will result in most of the sea ice underneath the surface to disappear. So when the sea ice under the surface disappears, it'll melt on top fast. There won't be anything left. So here we are at 2020. And this chart goes to 2030. But 1 degree, tipping point 1 degree. Well, we're almost there. It looks like. If we're not already. So there's that. Oceans absorb more than 90% of global heating. Here's global ocean heat content. Three-month average through October to December of 2019. Look how it zipped up. Zipped up there. Here's from 2010, 2020, and it's just zipping on up. As long as there is sea ice in the water, this sea ice will keep absorbing heat as it melts, so the temperature will not rise at the sea surface, but there is ever less sea ice volume left to absorb ocean heat, and the amount of energy absorbed by melting ice is as much as it takes to heat an equivalent mass of water from 0 to 80 degrees Celsius. And there's his explanation. He's explained this a lot about how long it takes for the ice to melt, and once it melts, it's, then the water just heats up exponentially. Once all ice is turned into water, all subsequent heat that goes into heating up the water will do so at 4.8 joules per gram for every 1 degree C the temperature of the water rises. So it's going to be a huge rise. The seas could be boiling. Meanwhile, temperatures keep rising globally, and more than 90% of global warming is going into oceans. Okay, tipping point number 3. Loss of sea ice albedo. Disappearance of the sea ice goes hand in hand with albedo changes that mean that a lot more sunlight will be absorbed by the Arctic Ocean instead of getting reflected back into space as occurred previously. The annual fall in Arctic sea ice is strongly influenced by weather conditions over the Arctic Ocean, as well as weather conditions over Russia and North America, as discussed in the next point. And in this chart, he says, Arctic sea ice extent has fallen strongly over the past few weeks to reach second lowest for the time of year on April 11th, 2020, second only after 2019. So that's the extent. So here he's showing where you've got snow and ice covering the water, and so when the sunlight comes in, it bounces back off. It's reflected off 90%, and only 10% goes into the water. But without any snow or ice on top of the water, we get, when the sunlight comes in, 94% of the heating rays go right into the water and heat it up, and only 6% comes up. So the more the ice melts, the faster it'll warm up, because there will be more open water without any snow or ice to reflect it back. Tipping point number 4, loss of terrestrial permafrost. Rising heat threatens to have a strong impact across the Arctic. One of the tipping points is abrupt thawing of terrestrial permafrost, resulting in loss of albedo, increased flow of hot water into the Arctic Ocean, and mobilization of large amounts of greenhouse gases. The Rutgers University image on the right shows a strong reduction in Eurasian snow cover in March 2020. So here it is. Snow cover. It's gone way down. The albedo changes due to decline of terrestrial permafrost are likely similar in size compared to the changes taking place over the sea ice. Furthermore, as the albedo feedback speeds up demise of the permafrost, huge amounts of warm water flow into the Arctic Ocean from rivers and groundwater in Russia and North America, also mobilizing large amounts of carbon and nitrogen, as a recent study indicates. Emissions across 2.5 million square kilometers of abrupt thaw could provide a similar climate feedback as gradual thaw emissions from the entire 18 million square kilometer permafrost region under the warming projection of representative concentration pathway 8.5, a study published in February 2020 finds. Tipping point number 5, jet stream changes. Wow, we've been seeing that. As the temperature difference between the equator and the North Pole narrows, the jet stream gets ever more deformed, resulting in more extreme weather events. So this is forecast for April 18th, 2020. Above image shows a forecast showing instantaneous wind power density at 250 HPA. That is on Earth Null School. The jet stream is crossing the Arctic Ocean, and 3 omega shapes show up that go hand in hand with warm air entering the Arctic closer to the surface. See, look at that. Here's the 2-meter temperature anomaly. This was back in, this was April 13th, 4.2 degrees C for the Arctic, higher than normal. I showed that. I showed that in my show. This can lead to strong extremes in temperature. Above image shows a forecast for April 21st, 2020, with cold weather over North America and high temperatures over the East Siberian Arctic shelf. Okay, so this is a forecast. Okay, he ran this on the 13th, but forecast it for the 21st. and we're seeing it go back up. High temperatures in Russia, Greenland, and parts of North America, such as Alaska, result in ever more fresh water entering the Arctic Ocean. Fresh water has a very low alkalinity or buffering capacity, which reduces the ability of the Arctic Ocean to take up carbon dioxide. A recently published study finds, which leads to the following point, i.e., loss of carbon sinks. So that's tipping point number 6, loss of carbon sinks. While the COVID-19 lockdowns have caused emissions have come down, especially emissions associated with transport and industry, greenhouse gas levels still appear to be rising at accelerating pace. Right. So this is Mauna Loa. This is CO2. Mauna Loa Observatory in Hawaii. Daily average CO2 was 417.85 parts per million on April the 9th. See, it spiked up there. As above image illustrates, the relentless rise in daily average carbon dioxide isn't slowing down. The rise actually appears to be accelerating. The annual peak in carbon dioxide is typically reached in May, so the recent rise can be expected to continue for some time. More extreme weather is causing stronger droughts, heat waves, and forest fires. This threatens to destroy farmland as well as forests that were carbon sinks until now. The boreal forests in Siberia and North America and the tundra within the Arctic Circle are particularly vulnerable, but also under threat are the peat fields and forests in Africa and Southeast Asia and South America. Forest fires in Australia earlier this year will have contributed to higher carbon dioxide levels. Extreme weather events over the permafrost could also have contributed in several ways, as discussed in an earlier post. And if you click on these links, these are posts of his where he's talked about these other things in detail. Important is also what happens in oceans. A recent study finds that one particular layer in the North Atlantic Ocean, a water mass called the North Atlantic Subtropical Mode Water, is very efficient at drawing carbon dioxide out of the atmosphere. Ocean warming is restricting its formation and changing the anomaly of the North Atlantic, making it a less efficient sink for heat and carbon dioxide. Indeed, more carbon dioxide may already get released from oceans than they can take up from the atmosphere. The Arctic has a pivoting role in this. Tipping point number 7. The image below shows the rise in methane levels at Barrow, Alaska. And this is the rise in monthly average methane at Barrow, Alaska, and that's the northernmost point of Alaska. So here it was over 2,000 parts per billion. Globally, NOAA reports a growth in methane levels of 11.54 parts per billion in 2019, the highest growth rate of the past few years. The image on the right shows an added trend, ominously pointing at a doubling of methane levels by 2026. That's not good. A doubling of methane over the next decade would have more warming impact globally than a doubling of carbon dioxide levels. These are marine surface data. The largest rise in methane has actually taken place at higher altitudes. The image below shows high methane levels over the Arctic as well as over Antarctica, with methane levels recorded as high as 2,755 parts per billion. One explanation for the high levels of methane over Antarctica is that wild pressure and temperature swings are causing cracks to widen and release methane. See, look down here. That's what it's talking about. So methane doubling in the next few years by 2026. Well, we're almost halfway through 2020. So I don't see how we can stand that. While fresh water generally is increasing due to increased melting, the Arctic Ocean can occasionally experience a huge influx of warm, salty water from the Atlantic Ocean. Changes to the jet stream make that stronger winds push warm water along the path of the Gulf Stream toward the Arctic Ocean, as discussed in a recent post. A recent study finds increasing current velocities in the European Arctic corridor, an increase up to twofold in North Atlantic current surface velocities over the last 24 years. Such an influx of warm, salty water could cause another tipping point to get crossed, i.e. the point where temperature rise at the sea floor of the Arctic Ocean and start destabilizing methane hydrates. This can occur when ice melts of the hydrate cages, thus causing methane to erupt, causing it to expand 160 times in volume when changing from a liquid to a gas. As the temperature of the oceans keep rising, the danger increases that heat will reach the seafloor of the Arctic Ocean and will destabilize hydrates contained in sediments at the seafloor, resulting in abrupt eruption of vast amounts of methane that further speed up Arctic warming. So here's the picture. So here's the heat coming down with the thinner sea ice or no sea ice, heating up those hydrates that stay frozen, and then they expand and then they blow up. And that's what Natalia Shakova has talked about, that her work is centered around that. Tipping point number 8, nitrous oxide and ozone layer decline. The image below shows levels of nitrous oxide as high as 354 parts per billion on April the 6th, 2020, with very high levels over Antarctica. Oh my gosh, look at that. That's awful. One explanation for the high levels of nitrous oxide could evolve around the presence of some very cold areas at the poles. Again, more extreme weather events, including wild temperature and pressure swings, could be behind this. Similarly, this could also be behind ozone depletion in the stratosphere. Well, and I will interject and say all the sulfur dioxide up there is causing the ozone to go away too. The Arctic is particularly vulnerable to a rapid temperature rise. Greenhouse gas levels are already very high over the Arctic. At the same time, hydroxyl levels are low over the Arctic, increasing the lifetime of methane over the Arctic. Furthermore, changes in aerosols can have a strong impact on Arctic temperatures. Black carbon settling on snow and ice hits the Arctic hard as it is speeding up warming. Without the dimming impact of other aerosols, the Arctic would have heated up even more in March 2020. Dust and sulfate currently mask much of the impact that high levels of greenhouse gas levels have over the Arctic. Tipping point number 9, falling away of the aerosol masking effect. Here we go. This is what Guy McPherson talks about. According to IPCC AR5, dust has a direct impact of minus 0.1 W2 square meters, while additionally contributing to aerosol cloud interactions. So that's the dust. This is from Null School. Above images show that in light of 550 nanometers as a measurement of aerosol optical thickness due to dust aerosols was as high as 8.9534 on March 28, 2020 at 7 o'clock UTC. The image also shows that quite a lot of dust ends up over the Arctic. Globally, sulfate has an even larger impact. Here's the sulfates. And we've seen that. We've seen all of this on CAMS. CAMS points it out in spades like this. As a result of the COVID-19 lockdowns, traffic in large parts of industrial activity have ground to a halt worldwide. The impact of shipping alone is huge, as discussed in a recent post. Nonetheless, sulfate levels can still be high, as illustrated by above image, which shows that light at 550 nanometers as a measurement of aerosol optical thickness due to sulfate aerosols was as high as 4.425 on April the 4th, 2020 at 1300 UTC. Right there. That's over Wuhan. According to the IPCC ARC image on the right, the direct cooling impact of sulfate aerosols is as much as minus 0.62 W to the square meter. Additionally, sulfate aerosols strongly contribute to the impact of aerosol cloud interactions, estimated at AR5 to provide as much as minus 1.2 W to the square meter cooling. Taken together, the two add up to as much as minus 1.2 W to the square meter of cooling. As said, sulfate currently has a strong cooling impact on the Arctic. As above image shows, reductions in the aerosol masking effect could make temperatures in the Arctic and globally rise abruptly and dramatically. Let's look at this chart. I haven't seen this before. So this is carbon dioxide, components of radiative forcing. Here's methane. Here's halocarbons. Here's nitrous oxide. Here's hydrofluorocarbons, and so on. A steep rise in temperature is in line with unfolding developments that are causing the aerosol masking effect to fall away, such as a decrease in industrial activity due to COVID-19 fears. The danger is illustrated by the image below. The image below shows a potential rise of 18 degrees C, or 32.4 degrees Fahrenheit, from 1750 by the year 2026. So here's 2026. Well, we're already at 2C, so he needs to revise this, because we're going to hit 3C. We could hit 3C before 2021. Above image was posted more than a year ago and illustrates that much of this potentially huge temperature rise over the next few months could eventuate as a result of a reduction in the cooling now provided by sulfate. In other words, a steep temperature rise could result from a decline in industrial activity that is caused by fears about the spread of a contagious virus, as also discussed in the video at an earlier post. Tipping point number 10. Further tipping points. Further tipping points can exist outside of the Arctic, such as changes to the monsoon in India and Africa, and rapid melting of the snow and ice cover of the Himalayas, which could temporarily cause flooding and eventually drought, famine, heat waves, and mass starvation, exacerbated by worldwide crop failure and by collapse of the Antarctic and Greenland ice sheets, which could cause flooding of coastal areas around the globe. The emissions that come with such further tipping points will hit the Arctic particularly hard, given the amplification of the global temperature rise in the Arctic. And then he ends all of his posts like this: the situation is dire and calls for immediate, comprehensive, and effective action as described in the climate plan. Well, I don't think that's going to happen. So there you have it, 10 tipping points for the Arctic. So we're in a world of trouble. Things are not looking good. not looking good at all. I will leave the link below to this article. I hope you got a lot out of this. This is quite sobering. We are living in very dire times, and nothing's normal. So I just don't see how much I don't know how much longer we're going to be here. I think if we make it to the end of the year, it's going to be a miracle. So I recommend that everyone get your spiritual houses in order. And if you haven't done so, no one knows the day or the hour, but it's coming fast. So until next time, God bless you. Go in peace, and I will talk to you soon.